All right, Algebra 2. Welcome back, guys. Here we go. We are in a brand new chapter, Chapter 7, and we're starting Section 1 today. All right, so have your notes out. Make sure you're copying all this stuff down. Start off on the right foot. You know what I mean? Let's start off strong with a brand new chapter. So here we go. All right, so we are talking about exponential functions, exponential growth, and exponential decay. All right, so exponential functions, those are going to be the functions that if you could look down here, they're going to make this type of graph, all right, where the graph is either going to start out really low and then go really high, or the graph is going to already start out high and then it's going to shoot down and go really low. Okay, so exponential meaning like it's just going to have a drastic change vertically, or it's going to have a drastic change going down. Okay, of course, exponential growth functions are going to have that type of shape, and then exponential decay functions are going to have that type of a shape where they go down. Okay, now let's learn a little bit more about like the equations that make it. All right, so here you go. You're going to want to copy down that. You got your exponential function roughly right there, looks like that. Base b, that's a constant value, so that's not going to be changing. But notice how x is an exponent, okay? So that changes this from looking like something that's linear, meaning just a straight line, to something that is drastically different, where you're not looking at x being a variable right next to the constant. X is now an exponent, okay? So these are some of the definitions. I've highlighted everything that you need in here, and I've highlighted everything you're going to need in here. So you don't have to copy down every word, but you have to copy minimum what I've highlighted, because that's the important stuff, okay? It's really important we understand this little word right here, the asymptote. Okay, so the asymptote is going to be the line that the graph gets extremely close to, but it never actually touches. Okay, so if we look at this graph right here, you're going to find that the asymptote is actually the x-axis. So you're going to have an asymptote where it's getting very close to where x is right there on the x-axis, which would mean that your y value is almost going to be 0, but it never fully touches the x-axis. Therefore, the y value never actually equals 0, but it's going to get very, very close to it. Okay. The next thing we have to really zone in on is this part right here for exponential growth. Okay, so your a value is going to be what is in front. Well, it's probably a little bit easier actually. If you think of your a value, I'll write this out here. Your a value, then your b value, and then your exponent right there. Okay, so think of it like that when they're saying a and b, and then x is your exponent. So if we are talking about a needs to be bigger than 0, that's this value. B needs to be bigger than 1. And if both of those things are true, you're going to create an exponential growth. All right, and then if we obviously have the opposite, then we're talking about, let's see right here, B is less than 1, but B is bigger than 0, then that's going to be creating a decay. All right, so B is never less than 0. B essentially is right there in between 0 and 1. It has to be less than 1. Got to be greater than 0. All right, so this next part here, this is going to be important when it comes to word problems, which unfortunately we're going to be seeing quite a few word problems in this chapter. Okay, so this is really helpful. So this is a good example for you guys to copy down. Okay, this is the generic form. So I highlighted everything that you're going to need for the generic, like no numbers. But this part right here, I want you to copy that down because that's a good example to have. All right, so let's walk through our example problems. First one here, anytime it says graph, graphing with the graphing calculator is all we're talking about here. Okay, So it is important to make sure you always are comfortable with how to plug the values in to your y1. Okay, so you're going to hit your graph and you're going to plug everything into y1 and make sure that it looks exactly like this when you're plugging that in. Okay, now you may wonder, how do I make x the exponent? Well, you remember there is a button that's on the far right hand side of the calculator, and it makes this little shape right there. You're going to push that button and then you're pushing X. Okay, so that's going to be very helpful. Now, how do we determine if this is growth or decay? It goes right back up to this here. Okay, is A bigger than 0 and B bigger than 1? And for this one, it is true. A is bigger than 0, B is bigger than 1. So therefore, this is going to be a growth. Okay, and then go ahead and graph that with your graphing calculator to graph it, so we won't need to waste time doing that in the video. All right, let's take a look at example problem 2 here. This is more of the word problem style that we're talking about. Again, you will have to use your graphing calculator once you have created the function. Okay, and that's this part right here when we're writing the function. All right, so as it says, we're talking about Australian humpback whales. I've highlighted what you really care about. All right, we have a population of 350. The 350 value is your A value. Okay, and don't forget the equation is A parentheses B and then brought to that X power. In this case, I actually would prefer it, instead of saying X, we're going to say to the T power, because T stands for time in years, and that's what we're talking about here is our population growth in years. So our A value is going to be 350. All right, that's the A. That's the initial value. That's what A stands for, is your initial value. Now your B value, what we're plugging into parentheses here, this is where this example problem is so helpful. Okay, so we're talking in this problem about an increase. So that's going to be everything on this side is important for you to understand because it's an increase. Okay, so we're going to have a 1, scratch that. We're going to have a 1 plus, and then what are we talking about? We're talking about a 14% increase. So how do you write 14% as 0.14 brought to the power of t? And we can simplify this one step further and say that this is 350 parentheses 1.14 to the power of t. All right, so this is our function. All right, so this is our f of x. This is our function. Now we have to graph this on the graphing calculator. Okay, so you have to plug this in for your y1. Now, something that I didn't mention yet is that your window is going to have to change, because you can see these numbers are going to be quite large. All right, because we're looking for when is the population going to reach 20,000. Okay, so at what time? So if t in this case actually represents x, okay, t represents x, and then your f of x is representing your y, then they are asking you 20,000, this is your y value, okay? So 20,000, this is your y value, and you're going to look, when do we hit 20,000 on the y value? What is our x value going to be for that? And what I'd recommend is you graph this and then use the table to get a really close number for that. So I've already graphed it, used the table, and the value that I was able to get here is about, I mean, we could probably round it up. It's about 31 years. Okay, so what your actual answer they're looking for, they need the function, that's this, and then the second part, they need the number of years that it's going to take to get roughly back up to 20,000 in the population when it started at 350. Okay, so let's do our last example problem here, number 3. I tried to highlight it in different colors in this one, thinking maybe that would be a little bit helpful to understand what's A, what's B, and then what's our actual function. So A has been highlighted in the yellow. Okay, so our initial purchase here is $1,000, but then you can see it depreciates, meaning it decreases. And this is going to be where you want to look at this part. Decreases, that's a depreciation. Okay, so let's go, and now we're going to have a 1 minus, because it's decreasing, at a rate of 15%, so 0.15, and again to the power of t for how many years we're actually talking about the depreciation. Now, simplify it. 1 minus 0.15, again, our initial value of 1,000, then that's going to decrease to a 0.85 to the power of t. So this is our function right here. So this is the first part that they asked of us. They said, write the exponential function. So we've done that. And now we have to graph it. Again, use the graphing calculator. So I've already plugged that in, and we want to figure out when it will fall below 100. So the second you notice in your table that the value falls, and again, we're talking about the y value falls below 100, the y value, what is your x value? Because t always goes with x. What is that value going to be once we just barely drop below 100? And when you plug that in, again, kind of rounding it, you're going to get about 14 years. Okay, so that's representing how long it's going to take for it to depreciate by a full $100 when the initial purchase price was $1,000. That's it. That's section 1. That's what I got for you today, guys. All right. So go ahead and, again, take the time to write down these notes. Watch all of these examples. Copy everything down. Ask questions in class if you got them. All right. We'll see you guys in the next one.